Hey everyone, and welcome. Today, we're going to talk about something that is, no exaggeration, one of the biggest updates to Java in years. I'm talking about virtual threads. They were finalized in JDK 21, and they are a total game changer for how we build big, scalable apps. So let's jump right in and see what problem they were even designed to solve.
You've probably been there, right? You build an application, it works great, and then a big traffic spike hits. All of a sudden, everything slows to a crawl. Maybe it even crashes. It's super frustrating, and it's a really common problem. So what's actually going on that makes our servers just hit this wall?
Well, the answer really comes down to a fundamental rule called Little's Law. It sounds kind of academic, but it's simple. It says that if you want to increase your throughput, handle more requests every second, you've only got two options. You can either make each request faster, or you can handle more requests at the exact same time. And that second one, that's concurrency. And that's where we hit our first major bottleneck. For decades, more concurrency meant one thing: more threads. But these traditional platform threads are really just a thin layer on top of very expensive, very limited operating system threads. Each one of these things eats up about a megabyte of memory just to exist. That means you can maybe create a few thousand before your server just runs out of steam. It puts this hard limit on your throughput way before your CPU is even breaking a sweat. So to get around this hard limit, developers got clever. We turned to this powerful, but let's be honest, pretty painful workaround: writing non-blocking asynchronous code. This was the old school way of trying to get that high concurrency without needing a bajillion threads. In the real world, this often led to something we call callback hell. You'd end up with code using things like complete future to do, where your logic is all changed together in these nested calls. It's not natural to read. It totally shatters that simple top to bottom way of thinking that we all prefer.
Oh, and the problems didn't stop there. This async style is just notoriously hard to write and even harder to debug. Your stack traces become almost useless because different little pieces of your code might be running on totally different threads. It's a maintenance nightmare that forces your whole team to think in this really complex, roundabout way. You just knew there had to be a better way.
And thankfully, now there is. This is where virtual threads come in. They are a new kind of thread designed to give us the absolute best of both worlds, that incredible performance we need, but with the simple code that we've always wanted to write. So what exactly is a virtual thread? Well, think of it as a super lightweight thread that's managed entirely by the Java virtual machine itself, not the operating system. The magic trick here is something called M-to-N scheduling. Basically, the JVM can run a massive number, the M, of virtual threads on top of a very small, fixed number, the N, of actual platform threads. This is why you can create literally millions of them without your system even blinking.
And when you put them side by side, the difference is just staggering. Look at this. The stack size goes from a megabyte down to just a few kilobytes. Startup time is thousands of times faster. And the maximum number you can have, we go from a few thousand to millions. The sense of scale here is it's on a whole different planet.
But here's the best part, the thing that makes developers so happy. Look at the code. With one simple change, like using executors.new virtual thread per task executor, you can go right back to writing simple, clean, blocking code that you can read from top to bottom. It looks sequential, it's easy to reason about, but it scales like the most complicated async code you've ever seen. The developer experience is just massively improved. Okay, let's get to the wow moment, because talking about it is one thing, but to really get the impact of this, you gotta see it in action. So we're gonna look at a test that really shows off the insane difference in throughput on a typical server workload. So here's the setup. We need to run 10,000 tasks. Each one of these tasks is gonna pretend to be a network call, like talking to a database or an API, but just sleeping for 12 seconds. This is your classic I/O-bound workload, where threads are just sitting around waiting most of the time. All right, so on the left, we've got our traditional setup, a thread pool with 12 platform threads. On the right, we're going all in with virtual threads, one for every single task. So how long do you think it's going to take each of them to get through all 10,000 tasks? For the platform threads, an unbelievable 2.78 hours. Yeah, you heard that right, almost 3 hours. And it's because it only has 12 threads to work with, so it has to chew through these tasks in tiny little batches. Each of those precious threads gets completely stuck for 12 seconds, just waiting. And now, for virtual threads, the grand total is 12 seconds.
No, that is not a typo. How on earth is that possible? It's because when a virtual thread blocks, the JVM just says, okay, you're waiting, step aside. It instantly unmounts it and puts another virtual thread onto that carrier thread to do real work. It wastes zero time. So all 10,000 tasks basically start at the same time and finish together 12 seconds later. Now that is the power of throughput.
Okay, that is just incredible performance, but let's be real. Virtual threads are not a silver bullet. To use this new superpower, you have to understand its kryptonite. You gotta know the situations where they don't help or where they might even cause some problems. For a long time, one of the biggest worries was a problem called pinning. Here's how it worked. If a virtual thread went inside a synchronized block and then did something that blocks, it would get pinned or stuck to its carrier platform thread. This meant the carrier thread itself was now stuck waiting, just like in the old model, which completely kills the whole scalability benefit.
But, and this is huge news, as of JDK 24, this major pinning problem with synchronized blocks is fixed. It's resolved. The JVM is now smart enough to work around this, which is a massive relief for pretty much anyone with an existing Java application. It makes adopting virtual threads way, way safer.
So what about tasks that are just crunching numbers nonstop? CPU-intensive stuff. Well, for a test like this one, you can see that virtual threads are actually a tiny bit slower. And why is that? It's simple, really. You can't have more things running at the same time than you have CPU cores. If your tasks are always busy using the CPU, virtual threads just don't offer any benefit.
All right, so let's do a quick fire round of key takeaways. First, virtual threads are so cheap, you should never pool them. Just make a new one every time you need one. Second, remember what they're for. I/O-bound tasks, the ones that wait, not CPU-bound tasks. Third, while the synchronized problem is fixed, pinning can still happen if you call native code. And finally, just know that they are always daemon threads, which means they won't stop your app from shutting down.
Look, if you remember only one single thing from our time here, please let it be this. Virtual threads are not about making any single task run faster. They are about letting your application handle a ridiculous number of tasks all at once. They exist to provide throughput, not speed.
And all of this leads us to one big provocative question for the future of Java. Now that we have this incredibly powerful tool that gives us back our simple, readable, thread-per-request code, do we even need the complexity of reactive programming frameworks anymore? That's a question the whole community is going to be debating for years to come, and it just goes to show how truly profound this new superpower really is. Thanks for joining me.